Hello, my name is Trisham Taylor. I'm presenting my thesis project extending the proof helper. The system I'm about to show you is the Math for Software Engineering proof helper system designed by Kristen Travis for her thesis project last year. This is the old interface. The system was designed to be used in conjunction with SC500 course Math for Software Engineering, in which students are required to build proofs. The system is designed to be a helper to help them build proofs, keep them on the right track, and keep them from having a false start. This is the previous implementation. As you'll see in a minute, I did not make a lot of changes to the implementation. My goal was to add functions, namely to add the ability to create new proof styles, to build quantification, and to perform predicate proofs. The previous system could only perform propositional proofs. Here is the new interface. As you can see, there are a few new buttons, a new proof styles menu on the top, and a new text field, which I will demonstrate soon. As you see, the file has open save. Students can save proofs to text files and load proofs so they can work on proofs outside of the system. And they can close, obviously, from the file menu. Edit gives you undo, redo, and the ability to clear a current proof just so you can stop and start over from what you're currently working on. And then proof styles is the next menu item, which I will get into in greater detail in the future. These are the proof styles that are now implemented for students to be able to build proofs in new ways. Down here, this is where a student would enter their expression, which I will demonstrate. And then to the left here are all the operators that can be used: equivalence, non-equivalence, conjunction, disjunction, not, implication, consequent, and then the new operators, universal and existential, are used to build universal and existential quantification respectively, and they actually represent conjunction and disjunction respectively. And I'll get into greater detail those in the future. So the system is designed to look similar to how a student will build a proof. This top line here is where the student enters the original expression. The student enters an original expression, and then every operation of the proof helper, whether it be a help function or a check function, requires a student to highlight a proper sub-expression of that expression, which can be the whole thing. And here I've implemented that if you try to student attempts to highlight something that's not a sub-expression, it won't let you, and you have to go back and highlight something that is, which P and Q is, but Q equals Q is not in this particular case. And then this box is where you want to show that it's equal to another expression, so you equivalence there, and then we put the justification. So we want to see how P and Q applies to theorem 3.35. You hit help, it gives you all the possible substitutions, and we choose no substitution, so P gets P, Q gets Q, and this now it's shown how that is applied. So here we have the new expression, and we add that to the proof, and we start with the new expression. Now, one thing we want to do is we actually want to show that all that new stuff equals Q, and what we can do using we want to start with the one particular side and make it look like the other. So I think we're going to start with the left-hand side. So that whole new expression that we just made, we want to show that it equals Q. So now we're given the information. This is what we want to show. So now the student knows where to go, what their goal is, and it's easier to keep track of their overall task. And then it's easy to compare what you have with what you want to have. And also, you can do the right-hand side as well. This is not really recommended to do both in the same proof, but I wanted to just demonstrate that it can be. Okay, for another example here, this is I want to give an example of a homework given in the course where students are asked to display the different proof styles, prove the same proof but using the different proof style techniques. So this is the problem, the original expression they started with, and then so here's the example. Nope, not here. Here's the example of the homework that would be given. So prove theorem 3.76, then E, it's blurry, and using these techniques. So the first one we're going to do is assuming the antecedent. So if you have something imply something else, if you highlight the implication operator and hit assumption, it'll give the antecedent, the first part, up top, and you start with the second part, the consequent, and now you can assume that that P and Q is true, and you can use that in your proof. So if you manipulate your proof to have P and Q in it anywhere as a proper subexpression, then you can assume that's true. So I'm going to apply a theorem here, and I want to see if it works. If I hit the help button, it does, and this is what so this is the new expression, and you see now I have a P and Q here, which is the same as the assumption. So there is a new function added, so if I know that the assumption, so if I just type the word assumption and then say, okay, well this is true because I know it's true from the assumption, the system will just let it happen, and it will check to make sure that the expression is actually the same as the assumption because it cannot be substituted. And if you hit the check button, yes, the system lets it go and adds it to the given proof. And so now true or P and R is a trivial proof to go forward. So we're going to move on to show another example. Proving by case analysis was not implemented because any implementation would either be too trivial or doing the work for the student. So moving on to proof by contradiction. Again, using the same expression because that's the homework assignment. In this particular proof style, you do not need to have anything highlighted. It applies to the entire expression, and now it says if you want to prove an expression, prove that not that expression implies false. Sorry, and so it sets it up for you, and it sets up the expression. So now it adds a not to the old expression and implies false, and then the student can say, okay, well I want to make sure this implies false, so I start with my left hand side, and now I want to make it look like the right hand side, which is false. And now a student can begin the proof as such. And I'm just going to clear this and show now proof by contrapositive. This one does need an implication operator highlighted, and what this says is that to prove something implies to prove P implies Q, prove not Q implies not P. So shown with a more complex example up top, and it does set up the implication for the student, and then the student now has the ability to start the proof as they see fit. Again, recommend to start with one side and make it look like the other. But we're going to move on and then show the last one, mutual implication. Last proof style just says if you want to show that P equivalents Q, if you prove that P implies Q and Q implies P, that will prove that they're equal. So this again just sets up, gives them two steps to do: P implies Q and Q implies P, and starts the first step for them, and then it's up to the student to know where to go from there. Again, this is not doing anything for them; it's just giving them a head start, giving them a heads up of how to begin. Okay, so now I'm going to demonstrate a quantification proof. I'm going to use a universal quantification. and I want to prove theorem 9.4a. Which is for all x, the range is q and r, and the body is p. And there I put 9.4a into the maximum value theorem number, so you cannot use any theorem higher than that number to help prove it, but you can use any theorem lower than that number to prove it. And so the theorem is that quantification equivalence for all x, where the range is empty, meaning true. The body is q and r implies p. And I want to prove that these two quantifications are equivalent. So again, I'm going to do the left hand side. So highlight the operator equivalence, choose left hand side, so the right hand side is put to the top, and I want to show that I can manipulate the left hand side to look like the right hand side. So I want to say, okay, equals, using theorem 9.2 with the substitution of r gets q and r, and in a second I will show you that theorem was documented by the textbook Logical Approach to Discrete Math by Griess and Schneider that's used in the course. Here is theorem 9.2, also called trading. It is an axiom actually, so it doesn't need to be proven. And here is the theorems go all the way up to the threes. All kinds of theorems. But in this particular case, we're going to use 9.2 with that substitution. So I will highlight the expression, hit help, and it says, okay, yes, this is how you would apply that theorem with that substitution, and that's what I get there. Now what I want to do is I want to manipulate the body, and the body is not a quantification, it's a propositional expression, so I can use theorems from chapter 3. In this case, I want to use, what was it, 3.65 with those substitutions, and then I think I decided, yes, I want to show you the theorem that I'm going to utilize here all the way to the top, 3.65, also called shunting. So I'm going to use this theorem to manipulate the body of the quantification. So I highlight just the body because the sub-expression I want to manipulate, hit help, and now that applies the substitutions to that theorem and shows what my new expression will look like. So it only worried about the body, but then applied to the whole quantification. Now, if I just show what I want to start with and end with and not have the justification theorem, it will tell me possibles, but I made a mistake there. I highlighted the entire quantification, not the body, which is what actually needs to be changed here. So I should have highlighted the body, and my past self will figure that out now. Yes, there we go. So highlighting the body, try it again. Now it says that theorem applies with those substitutions to the two expressions I gave it, so now I can add that to proof and it works. So now here I have this expression, and I'm pretty sure that if I apply theorem 9.2 once again with the substitution that r gets q and p gets r implies p, that it should work. So I highlight the expression, hit help, it does. It gives me the expression, and look, that expression is my right hand side. So I have successfully completed the proof. There is no indicator that you have. It's up to the student to recognize that what they have looks like is the same as the right hand side. Alright, I'm going to clear that. And now I want to demonstrate a much more complex example. Oh no, this is not a complex. This is just showing with substitutions. Instead of using the letters R and Q, now my range is I is less than 0 and my body is negative to I, so that's a predicate saying that you can make up anything you want pretty much as a predicate, saying that the I is negative if it's less than 0. I check to see if it applies to theorem 9.2. It does with those substitutions, and then I can, so now that means that I less than 0 implies is negative that I for all I. So that's how you would read that, and just a demonstration of just a more complex example, not just using R and Q. Now the operator I'm going to use here is plus. Now quantification can use any associative and symmetric operator, addition, multiplication, minimum, maximum, conjunction, and disjunction as we've seen, but those are used with universal and existential. And now what I have here is where the range is pretty complex, and actually I'm demonstrating theorem 8.20, which I will show the theorem, but with instead of x and y I'm using I and j. My ranges are that whole mess of 0 less than or equal I, less than or equal j, less than n, and the body is just f of f dot j dot I. So some function utilizing the dummies j and I. At this particular point, we don't care what the function is or does. We just want to show how quantifications can be manipulated. So here I have one quantification equals another, and then I'm going to want to show how the left hand side can be manipulated to look like the right hand side. And you'll notice that the body of the second quantification is actually another quantification in and of itself, and that is possible, that's allowed. And you can see in the theorem 8.20 there, that is, it's called nesting. This is actually an axiom. I call it a theorem, it's an axiom. And I want to show how this can be applied. So okay, I highlight the equivalence. I want to start with the left hand side, so it displays the right hand side for me, giving me the operator. And now equivalence. Now here's something, another feature. If you type in arithmetic, there are some things, sometimes you want to manipulate ranges or manipulate numbers that the system isn't going to recognize. I want to show that this range can also be written as something and something else, and the system isn't designed to recognize that, but it is designed to say, well, okay, if you say it's arithmetic and you as a user say this math works, then I trust you, and it's up to you to be correct. So it's up to the user in this particular case to know what they're doing is correct, and the system will not question. So if you have arithmetic as justification, highlight, check, it says okay, good, and it puts it up there. Now, okay, I say, well, I think I can make it look like the right hand side now equals the right hand side, but I'm not exactly sure what theorem, what justification. If I hit the help there, it gives me 8.20 with all those substitutions, and it does work. If I hit check, it would work. So there are some features, and now here's where you could load a completed proof and check to see if it'll check to see if it's right by checking it step by step. And thank you for watching my demonstration of the changes I made to the proof helper system.